everyone, and welcome to my presentation, Overcoming Challenges for the ASTM List of Elements in Cannabis and Hemp Flower by Microwave Digestion and ICP-MS Analysis. My name is Aaron Heineman, the Inorganic Product Line Leader for PerkinElmer. In this presentation, I will look a little bit closer at the technology, sample preparation, sample analysis, and validation guidance for the determination of metals in cannabis products. So when I talk about cannabis and those related products, what do I really mean? Well, there are a variety of forms that can be found on the market, from flour, butter, concentrates, edibles, and ointments. Many jurisdictions are referring to the work that the International Council for Harmonization compiled in their guideline for elemental impurities, known as ICH Q3D document, or the guidelines for ICH Q3D. These are referenced by the United States Pharmacopoeia in Chapter 232. This guideline sets out the elemental impurities and their maximum levels based on the route of administration. For cannabis, the applicable limits are typically inhalational for inhaled substances and the oral routes through ingested substances. Here you can see a table of elements monitored based on the jurisdiction or based on a reference document such as NIST, AOAC, and the ASTM study. In this work, we looked at the entire list of elements. You can see here on the left-hand side of the table, which expands on our previous work, which focused on the big four elements, which would be arsenic, cadmium, mercury, and lead. Now, let's take a look at sample preparation. Cannabis and cannabis-derived products, as you know, come in a variety of forms. So some of these forms can be quite challenging to prepare, either to mix or homogenize, or actually even subsample some of these. Can be difficult. To help laboratories with the full analysis, we've maintained a verified method for the determination of elemental impurities in cannabis and cannabis-derived materials by closed vessel microwave digestion and ICP-MS analysis. This is a way to help laboratories get ready faster. Our provided SOPs will give you information on how to prepare samples, how to do the microwave digestion, how to prepare the standards and quality control solutions, how to set up the analytical method on the instrument, and how to begin a run. This method would eventually form part of your quality management system and a laboratory's final SOP that they would eventually get validated. Again, this was primarily focused on the big four heavy metals, so there are minor modifications such as different standards to be used to analyze the complete list of elements. So one important aspect of testing anything, especially natural samples or food type samples, is the homogenization, as I indicated earlier. We want to obtain a representative sample and result in a more complete digestion in the end. So we will cut, grind, pulverize our samples as much as possible. Distillates, for example, can be really thick. In the case of distillates, we typically warm them up so they're a little less viscous, so we can homogenize them and then take a subsample. Edibles, you typically want to either finely chop the edibles or even cryogenically mill them. That's a great way to homogenize those sample types. And some other method considerations here. Is it a solid? Is it a liquid? Is it an extract? Is it a volatile? Is it a wax? Is it hydrophobic? Many of the waxy extracts can be difficult to digest. So depending on the jurisdiction, you also may have a certain weight or mass of the sample that you need to prepare and digest. Currently in some jurisdictions, a half gram is required. In New York State, for example, they are referencing 0.125 grams in their method, so you need to be considerate of that. Also, something that really needs to be considered are the reagents that are used for the preparation. The cleaner the reagents, the lower the background, the better the results usually. So for all of our work that we've done so far, we the Titan in the system, the vessels inside there are made of very high quality, high purity, very low porosity TFM, PTFE material, resulting in very low carryover from sample to sample or digest to digest. And I have some method blank data I prepared before. I can show you shortly. So in the provided method and operating procedures, the sample preparation guidance is to weigh approximately 1/2 gram of sample. And for the work shown here, we weighed all samples in the range of 499 to 501 milligrams. This makes it easy and consistent from sample to sample. We then add gold to help stabilize mercury and add any matrix spikes at this time to assess matrix recovery or when performing method validation. We would then add nitric acid and peroxide to each sample, allowing the samples to react. Then we allow for some pre-digestion, and then once that reaction has subsided, the vessels are then capped, they're closed off, and put into the microwave for digestion. A typical digestion is shown here on the slide. And then once digested, the vessels are allowed to cool, and then the sample volumes are made up to 50 milliliters. Regarding that pre-digestion step I discussed, we will typically allow anywhere from 10 to 45 minutes for samples to be exposed to the acid prior to capping the vessel. This allows us, first off, to identify any very reactive samples. So if they're very reactive samples, we may want to treat them a little bit differently or allow the pre-digestion to occur longer in order to evolve the CO2 that is generated from the oxidization from the nitric acid and peroxide. This, allowing the CO2 to evolve with the cap off, prevents overpressurization of the vessels during the digest. In the end, after all the digestion, what we want is all the digest to look the same, a nice clear digest state. Occasionally you will see some yellow left in there due to some carbon residue, but ultimately what we want is a clear digest state with no remaining particulate matter. Here are some examples of some digests that we've performed on flour, cookies, oil. In the end, take a look, they're all clear digest states. Okay, so now we'll talk about the instrumental analysis on the next in ICP-MS. So why do we use ICP-MS? We're using ICP-MS because we can hit those lower inhalational PDEs, or permissible daily exposure limits, or the detection limits based on jurisdictions for the Big Four. Those limits can be particularly challenging for ICP-OES, and especially at the dosage levels that many jurisdictions are going with. Graphite furnace and hydride analysis could possibly hit the required detection limits. However, those techniques to prepare samples for those techniques is much more laborious. You have to run the samples multiple times, and different sample preparations would be required. For the Big Four heavy metals, you can determine them in about 1 to 2 minutes, depending on the instrument configuration. In fact, it doesn't take much longer to add analytes to the method, as most of the time is spent getting the sample in and out of the plasma. Okay, so here are some example instrumental conditions. These are instrumental conditions used for some of the data that's shown later. Note that helium is used for KED mode. KED mode stands for kinetic energy discrimination, or collision mode. It was run at 4.3 milliliters per minute, and the resulting all matrix solution or aerosol dilution was in the range of 2.5 to 3 for this method. So for any ICP-MS work, I typically recommend a flow injection setup. And the reason is the use of flow injection, like the HTS shown on this slide, reduces deposition on the cones, reduces argon usage, reduces turnaround time for the data, reduces mercury carryover, and overall sample-to-sample time. For example, the method used for this work, for all these extra analytes added to it, is about 2.5 minutes with the HTS and about 4 minutes without. So again, important to consider what matrices you're preparing in regards to your sample analysis. All these digestates in this particular digestion scheme result in a fairly heavy matrix. So there's quite a bit of acid in there, and the total dissolved solids in there from the sample, there can be quite a bit, depending on the preparation and the sample type. Note, the preparation factor is approximately 100, since we're preparing a 0.5 gram into 50 milliliters of final volume. In theory, the total dissolved amount of solids is a maximum of 1% in this digestion scheme. So I typically recommend the aerosol dilution technique to reduce the plasma loading. This avoids bench level dilutions and is much more efficient for laboratory operation. For aerosol dilution, Nexene uses something, as I said before, called all matrix solution, or AMS. This allows the user to introduce a flow of argon into the neck of the spray chamber. The dilution of the aerosol allows for more efficient ionization of the sample as it enters the plasma. This results in much lower suppression, reduced suppression, and fewer physical and matrix effects overall. In addition, less deposition on the cones, which means you can run for longer without having to do maintenance. The analytical procedure overall is fairly straightforward. As indicated earlier, it's a fairly simple preparation and of the multi-element calibration standards that cover an expected range of the samples. We also recommend the use of an online edition of an internal standard solution to correct for the different matrix effects due to the different sample matrices. Here on this slide, you'll see a list of isotopes and elements monitored for this work. Everything was run in one mode at a constant flow rate of helium, as shown in the instrumental conditions table. The reason for that is efficiency. It's faster that way. The internal standard elements are shown in the table on the right. Of particular note are the elements that we monitored multiple isotopes for confirmation, also the elements with and without dynamic half-mass correction technique. Okay, so a lot of people have brought these questions to me before, and this topic has come up before from a few customers and researchers about plant material and doubly charged interferences. Most doubly charged ions are relatively low in concentrations in cannabis samples, so in general we found them not to be problematic. But if a sample contains a higher concentration of barium or rare earth elements, doubly charged ion interferences will contribute a significant number of counts, leading to false positive results potentially. In addition, when using collision mode in ICP-MS, the relative contribution of the doubly charged ions will be greater due to its larger mass. By monitoring the isotopes of barium, neodymium, samarium, gadolinium, and dysprosium, the potential interference from doubly charged ions on zinc, arsenic, and selenium can be estimated and corrected for using equation correction technique. This type of doubly charged ion correction requires multiple steps and is time-consuming to set up. Using the singly charged ions to estimate the formation rate or for doubly charged ions is also prone to errors if the ionization conditions change, for example, due to different sample matrices. Therefore, to streamline analysis and improve accuracy, we recommend the use of dynamic half-mass corrections. By using this type of correction, the system can automatically correct for the interfering element by monitoring an alternative half-mass of that element during the analysis by using resolution less than or equal to 1/2 of an AMU, or atomic mass unit. This resolution is easily set up in the system optimization. Here is a result of the corrected and uncorrected barium doubly charged on zinc 66. As you can see, there isn't any significant interference on barium in the parts per million until barium is in the parts per million levels in the digestate. Note, for all the samples that I tested during this study, the zinc concentration was much higher than the barium concentration. So this was, barium was of no consequence to the analysis. So here is the result of corrected and uncorrected neodymium and samarium doubly charged on arsenic 75. As you can see, there isn't any significant interference until both the neodymium and samarium are in the high parts per million in the digestate. Note that they both interfere relatively similar levels with 100 ppb total of the two rare earth elements, which resulted only in approximately a 10% bias in the arsenic results. Note, for all samples I tested, arsenic concentrations were higher than 5 parts per billion. It was rare for neodymium and samarium to be in the high parts per billion. Very rare to see it at all. In fact, the only samples that were tested that had the elevated neodymium or samarium that caused any significant difference between the corrected and uncorrected values were, in fact, NIST reference materials, the peach and tomato leaves. We've seen this also in some tobacco samples we've tested. So here's the same bar chart of corrected and uncorrected dysprosium and gadolinium on doubly charged on selenium mass 78 specifically. As you can see, there's little more influence from dysprosium and gadolinium on selenium than with arsenic and zinc, so it is a little bit more of a potential issue. But note, again, for all the samples I tested, the selenium concentrations were lower than 5 parts per billion in the digestate, and so no significant interference. In addition, gadolinium has relatively larger interference than the other doubly charged interference have, with a factor of about 1.4. For this work, here are the equations used in the method. It contained dynamic half-mass corrections, isobaric corrections, and also included an equation that sums up lead 206, 207, and 208 to account for variations in the isotopic distribution of lead on this planet. Okay, now I'll review how one would go about validating this method and show you some example data, summary data. So for those of you familiar with AOAC, AOAC has published SMPR 2020.001. This is a standard method performance requirements for the determination of heavy metals in a variety of cannabis and cannabis-derived products. In here, they have validation guidance in the document. It refers to USP Chapter 233. It requires that the big 4 elements, arsenic, cadmium, mercury, and lead, have an LOQ of equal to or less than 10 parts per billion. The other metals are noted as optional, as it covers multiple jurisdictions. An important part of this SMPR is that the method performance is based on the concentration ranges determined, which to me makes sense. Okay, since that refers to USP Chapter 233, I'll talk about it here. So if we go to 233 and compare it to what the AOAC has talked about, USP Chapter has information on how to determine repeatability, ruggedness or reproducibility, and accuracy. You can then combine the USP guidance on how to determine these validation parameters with AOAC's performance requirements to establish a validation protocol. And that's what we did here for the example validation and example data. So the first thing that we did during this was the determination of the limit of detection and limit of quantitation, which isn't required by USP Chapter 233, but is useful when needing to report data. This was performed by taking 10 digested method blanks and multiplying the standard deviation by 3 for the limit of detection and multiplying the standard deviation by 10 for the limit of quantitation. We use this to understand the variation of background contamination in the vessels themselves and understand what our reproducibility is at the lower end in the digested vessels themselves. So if you look at our mean values on this table, they are all less than the limit of detections, which is good. There's no vessel contamination above our limit of detection. Note that all these values are factored up to the parts per billion or micrograms per gram using the 100-time preparation factor of the method. The first two data columns contain the ICH-Q3D inhalational and oral limits based on a 10-gram dose. So you can see that the LODs and LOQs are significantly lower than the PDEs because of the sensitivity inherent in ICP-MS. Next, we performed a repeatability study that is referenced in USP Chapter 233. Chapter 233 says that 6 replicates of a cannabis flower material or whatever material you're trying to validate need to be spiked at 1 times the limit, which is called 1J in USP speak. So in this case, we took a sample identified as flower A, homogenized enough of material to do many replicates. We ended up with a very well homogenized sample, and you can see how finely ground it was in these images here. And then on the table to the left, you can see the mean concentration of the analytes derived from triplicate preparation of the flower, as well as the repeatability of 6 replicate spiked at the standard 3 level. So we just picked the middle standard, spiked at that to look at the repeatability of recovery. All of the RSDs were well within the repeatability requirements stated by AOAC SMPR guidelines. And for the recovery study, we looked at mean spike recovery of the studied elements for the 6 spike digests of cannabis flower A sample. You'll see on the right the AOAC SMPR indicates from 10 to 100 part per billion spike recovery should be within 60 to 115%. For anything above this, recovery of the spike should be within 80 to 115%. In the table, I have the mean concentration found in the unspiked sample that was prepared in triplicate, the spike level, and the mean spike recovery. And all spike recoveries were within the target range. Note that arsenic, selenium, zinc were half-mass corrected values. Also note that the spike levels for barium, copper, and zinc are basically invalid. They're not high enough. They were too low to really differentiate between analytical variability and spike recovery. There's some data here. I know it's a bit of an eye chart. This is the quantitative results from 9 different cannabis flower samples, A to I in here. Also shown for reference is ICH-Q3D inhalational limits, assuming a 10-gram daily dose. The standard deviation on cannabis A sample is shown, and at the end I tagged on a random tobacco sample provided by one of the lab staff. Note this tobacco sample is only from 1 cigarette and is definitely not representative of all cigarettes. Also included in this table are half-mass corrected values versus non-half-mass corrected values for arsenic, selenium, and zinc. I've highlighted, I believe I've caught them all, and I've highlighted the results that would have failed ICH-Q3D inhalational limits based on a 10-gram daily dose. Common over limits were with nickel and molybdenum. I really find it interesting and suspect it's due to elevated levels in, I'm thinking, the fertilizers they're using. For information purposes at the bottom, I've also included the rare earth elements that were determined. Here is the same table. However, I've pared it down with the relevant rows that pertain to the dynamic half mass corrections for rare earth elements. As you can see, the arsenic and zinc corrected and uncorrected match fairly well, indicating that interference is basically insignificant. However, with selenium, there were some notable differences with the corrected result, indicating gadolinium concentrations should be monitored and corrected for. Part of every laboratory quality management system should be regular proficiency testing. We have been participating in the Emerald test for heavy metals since 2018. This year, they now have a heavy metals in hemp oil PT as well as a heavy metals in hemp flower PT. So be sure to enroll in proficiency. In summary, ICP-MS in combination with an optimized digestion protocol is easy and reliable way of testing cannabis products for metals and heavy metals and other elemental constituents in these samples. ICP-MS limits of detection and quantitation were well below the inhalational limits for ICH-Q3D based on a 10-gram dosage. All the validation data was within AOAC standard method performance requirements, and also rare earth elements can be found in some plant materials, likely depending on their growing conditions. In particular, the gadolinium on selenium interference should be corrected for. That's it for my talk today. If you have any questions, please feel free to populate them in the questions pane of the system, and we'll get to them at the conclusion. Thank you.